now we switch the topic to CSU2. So there's 2 is 2 stage, right? So the first stage is the same as CSU1, and now we have stage 2 sampling. So we have stage 2, which is simple random sampling of MI elements from the capital MI elements in cluster I. And so that means we cannot really observe TI, the total, but we observe its estimator. We can compute its estimator. So this is the sample mean, right? Sample mean of Y in cluster I. Okay. For point estimation, we use the same formula for PPS sampling using t hat. So the only difference is that previously we have, right? Previously we observe TI, but now we don't observe TI. So we use estimator TI hat and construct capital K. Okay. So the form itself is essentially the same. The sample mean of T hat case. Okay. So basically, step 1, you compute T hat K. So that's the most important one. So that is Ti divided by Pi if Ti is known. If not, then small use Ti hat. Okay. So that's step 1. Step 2, you compute this, take the average, right? Step 3, compute the variance estimation. So that's it. So and now this T hat K, so this and because we have AND row and independent rows, so that means for each row we observe 1. So this is case row. So for each row we observe 1. We can observe 1 T hat, and this T hat is actually from follows this distribution. So the expectation of T hat is what? Summation I equal to 1 to Ni T hat I divided by Pi times Pi, right? And so that's becomes, so that's about okay. And then if you take expectation, so this is the expectation of 1 with respect to the first stage sampling, and then the second stage sampling. If you take the second stage sampling expectation here, then you take the expectation here, and then this one becomes each one, right? Each one is Ti. So you end up getting the unbiased estimation. So so that's so the idea, the point estimation. The nice thing about this is that the point estimation exactly the same structure as the single stage, and variance estimation formula is the same because of this, because the fact that these T hat 1 to T hat n are independent IID sample, so they are IID. So this fact doesn't change even for two stage sampling. So that means we can still use this formula. Okay. So that's nice. So variance estimation formula is essentially the same as the single stage case. Okay. So now I'd like to use introduce a special case of this sampling design. It is a so that is very popular one. The main feature is this. We use the same number of elements in the second stage sampling for sampling. So the estimation of a mean, we see that this one. Okay, let me write it here. PPS2 is T hat PPS2 divided by, so 2 means the second stage, okay? I mean 2 stage. So n, right? And then that is, you can write it as a T hat k divided by n. And so let's call this as a ck. Okay, and then note that T hat k is actually T hat I minus what? Minus pi, right? And T hat I, what is pi? Pi is, by the way, mi divided by summation of I equal to ni mi. So that is mi divided by n, the population size. So basically this, you can write it as a, divided by n. Okay, and so that means from here, if you use this definition, ck is T hat k divided by n. So that means T hat I divided by mi. Okay, so that's this one. So in the end, you this is just 1 over ni z, I'm sorry, y bar I is the index for the case selection. So you can actually write it, if you remember, this is ak is the ak equal to I. So we can define ak equal to I. So if you introduce this notation, then we can write the y bar PPS2 as a average of y bars, right? So that's kind of interesting expression, because it's just the mean of the cluster means. Okay, and now if y bar, so now the point is that if this guy is a mean of m observations, right? So sample mean of the m observations, then you can actually write it. So this is because of m. So you can actually make this summation go outside. So m goes outside of summation, and you end up just writing the whole computation becomes very simple. So basically, it's a sample mean in after the two-stage sampling. Of course, if there's a duplication in the clusters, then it's a little bit different story. But suppose there's no duplication, and this is the case when ni is sufficiently large, then the chance of selecting the same cluster in the sample will be very low. So we'll just use this one. So if you write it, this expression means that samples have all equal weight. So that is called this self-weighting design. And then variance estimation is still use the same simple formula, because this is the sample mean of the z's. Okay, so we just use the 1 over n times sz, where z is this y bar I. So variance formula of the sample means. So that's the exactly this formula is about. So this sampling design is very popular in practice for several reasons. First, use of the this one pi equal to proportional to mi makes the resulting estimator efficient. That means a small variance. Small variance, and the point estimation is easy to compute as the weight is are all equal. Furthermore, if we give one sample cluster for each interviewer for day's workload, then the choice of mi equal to m make the workload all equal. So which is very convenient for the survey operational purpose. And variance estimation is also very easy to compute.